Hello everyone, my name is Emiliano Larach, and today I'm going to be walking you through lab number 3 for Physics 2212, which deals with magnetic fields of a Bauer magnet. First, on this lab, we are going to be exploring the relationship between magnetic fields and observation distances on axis and perpendicular to axis, specifically relating how distance affects a magnetic field. We will also be going over Biot-Savart law and modeling magnetic fields computationally. Here's the Biot-Savart law so you can see it. We will reference it ahead. First, going ahead to our results, my magnetic dipole moment was 2.56 joules per Tesla, and my magnetic field proportional to distance was minus 3.6 power. First, our experiment, we download the app called Teslameter, and we determine the direction of the magnetic north until our x component was 0. You can see this is the closest I could get it to 0, and this was important for offsetting Earth magnetic field. Then I located the magnetometer of my phone by moving it next to a ruler on the x and y axis and looking at the highest points of the x and y axis magnetic field. And I determined that my phone's magnetometer was in this corner. Then we recorded the magnetic field reading from the phone at various distances from the magnet into the provided spreadsheets at different angles, so at in-axis and off-axis. So the physics model we will be talking through, explaining is the Biot-Savart law, and the magnetic field represented as B is a function of the magnetic dipole moment, our observation vector, and the magnitude of the magnetic field can be expressed as kr to the n power. And our n is expected to be minus 3, but we will see we have some percent error in this that we will discuss later. So since we now know how to calculate the magnetic field of the magnetic bar, we used our data from our experiment to find k and n. And these are our on-axis measurements. We found our k to be e to the negative 1.5 power and our n to be negative 3.56 power. So negative 3.56. Our expected value was of 3, so we have a 17% error. We see it's moderate for this kind of experiments where we're not in like a controlled environment. Then for the off-axis magnetic measurement, we found that our average D-perp was 0.18 meters and our average B net was 1.68 times 10 to the negative 4 Tesla. So our D-perp is this distance and the magnetic field average at those distances. We then used Glowscript to define the Biot-Savart law and to create an observation point at 45 degrees in recalculating our dipole moment from there. Our results varied from our measured results that we got from like our experiment, and our computed values from Glowscript. Glowscript varied significantly, as you can see in the screen, but this is to expect in experiments like this. So my Glowscript output was this. You can take a look with a more paused look to it if you want. And then we saw there were some varying aspects to our experiment, and this is because of multiple error sources. Some of them can be the location of the phone's magnetometer, that I didn't find it correctly, and not completely offsetting Earth's magnetic field. That's the thing that where x had to be 0, and maybe that was not that didn't offset Earth magnetic field enough. Then the two discussion questions. First is, what if you hadn't oriented your experiment to compensate for magnetic north? And I think all of the readings would have had an interfering field from Earth's magnetic field, so all of our values would be skewed to a certain direction, and our values would be less accurate. And then what if you were to stick two identical magnets together end to end? So we know that the length of the magnet, we can take it as a not like very considerable. So our magnetic field direction will be exactly the same, but just its magnitude would double, because we have one of the extreme cases where the length of the magnetic dipole is much more less than the observation point. So then as a conclusion, I have that a magnet behave as a magnetic dipole, and thus their magnetic fields can be approximated with the Biot-Savart law. and the distance considerations, that its intensity decays over time, over distance. And then, as I said, distance is very important when taking into account magnetic fields. This can be applied to real life. In real life, if we have some cables that are generating magnetic field, those cables do not affect us because the magnetic field is very, very low compared to the distance we are from that cable. So that will be all for my lab. Thank you very much for watching, and I hope you enjoyed it. Bye.